Good morning, everyone. Welcome to our seminar. It is today a special day for me because it's a great honor to introduce our speaker, Professor Eric Fossat. And also it's a pride because Eric Fossat has been a long-standing collaborator of myself and of our group at the IC for the last 30 years. And despite this, he is one of my best friends for these 30 years. So Eric Fossat is emeritus astronomer at Observatoire de Nice, de la Côte d'Azur. All his career has been developed between Observatoire de Nice and the Department of Astrophysics at Nice University. So the word emeritus means that he is now retired formally, but I promise you he's as active as he has been for the last 50 years in different fields of astronomy. Eric is not an orthodox astronomer. It's very heterodox in many aspects. He is brave, taking a lot of challenges during his scientific life, and pushing forward very important projects during these 50 years. Main fields of research of Eric have been moving from characterization of the atmosphere of the Earth for astronomical use, characterization, and helioseismology, and further astroseismology. And he has been moving back and forth from these fields, and just recently he just came back to the helioseismology field, in which today is going to present very new, attractive, novel results, and I guess they are just ready to be accepted for publication.
Yes.
Yes. Not fully confirmed, but yes, it's coming.
It is accepted with minor revisions.
Well, okay. So, as I told you, Eric has been involved with us since the late 70s. We were competitors until '89. In fact, the three pioneers of helioseismology in Europe, and I would say worldwide at this epoch, were Professor George Isaac at the University of Birmingham, in which we start to collaborate, I see. Professor Teodoro Roca Cortés is here at the AC, and the third pillar, and very important as well, has been Eric Fossat. In '79, he imagined how powerful helioseismology information can be for understanding the interior of the Sun. So he convinced someone, Martin Pomeranz, to go to South Pole in '79 to observe continuously the Sun for a few days, less than a week. Of course, you can imagine that the results were excellent. Unfortunately, just 2 months before this famous Nature publication took place, the publication on Nature of Claverie et al. With Teodoro Roca Cortés, the origin and the establishment of the nature of the solar P-modes at that time. Since then, he has been doing many things. One very important in which I was very involved, and not only me, but other people at the IC, was to establish the first global network for helioseismology on Earth. It was called IRIS. IRIS is also the name of a flower. So, important thing is that we managed to run a limited network of 5 stations in which our priority was not only science, but also to establish new relations with emerging communities, like in Morocco, like in Uzbekistan. So aside from a scientific experience, was really a human experience. The science manager of the IRIS network was Bernard Gelly, now it's the director of TEMIS, and many people get involved. So, well, I can talk for a long time about Eric. I will stop, sorry. Main point is his talk. I think it's very interesting, and please, Eric.
Muchas gracias, Pere. You hear me okay? Yes, I have some problem with hearing, so I'm not sure if it's okay. You tell me it's okay then. So, okay, I will try today to convince you that we have detected asymptotic G-modes on the Sun, and that with these asymptotic G-modes we have now some numbers about the solar core which are unexpected in accuracy. So, you are all astronomers. You know that we have invented fantastic tools for astronomy. I illustrate just two or three of them. You know this one. You know this one. With these tools, we know this one. And with these tools, we are able to do fantastic things like observing the central black hole in the galaxy, like observing the beginning of the universe, things which are fantastic. But if we come back to the Sun, we can just observe the solar surface, and we cannot see inside. Any big tool you can take, you will not see inside the Sun. So that was extremely frustrating for astronomers, because astronomy is a science of observations. We are not happy if we are done deducing something from equations. I'm not happy if I'm deducing something from equations. I need to see. And to see inside the Sun, it's just impossible. That's why we invented helioseismology. We know, of course, many things about the interior of the Sun. We know there is a core. Let me see. This is, yes. We have a core with 15 million degrees. We have a stable layer of radiative propagation of energy from inside to outside. We have a turbulent upper layer of convection. All this we know, but as long as we don't see and measure it directly, we are not happy. I don't speak. And for happiness, this is the solar surface that you all know. This solar surface is very turbulent, convective, blah 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 blah, and the blah 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 is acoustic noise. This acoustic noise is able to make resonance of the sphere, and that was, we can probe the solar interior thanks to this resonance. This came out in the early 70s, the general ideas, and as Perret told you, the first real observation which made it possible to identify at least one and many frequencies of resonance came by the end of the 70s, especially when Mark I started to measure here, and we made our measurements at South Pole. And the measurement at South Pole was in between 79 and 80, because it started on December 31 at 10 p.m. in 79, when everybody was drunk, of course, 10 p.m. But the sky was clear, the instrument was ready, on, and that was it. This is a souvenir of South Pole. This is me, as you can see, or you can guess, maybe. Then the general ideas, indeed, this noise of acoustic convection is making acoustic resonance of the Sun, and so we tend to compare this with the music, of course. They are not musical sounds, but they are musical waves, very low frequency, and these musical waves gives access to the knowledge of solar interior, as well as, if you listen to music, you have the knowledge of where are the instruments, which instruments are there, and so on. Same kind of information. So that was fantastic success. This I skip. But the fantastic success has some limitation. The sound waves have this structure. If you hit the Sun here, you have waves propagating inside, and most generally avoiding the center, because with the increasing temperature inside, you have increasing sound speed. So if the wave is not exactly horizontal when it penetrates inside, it will be refracted and move up. So almost all the waves, acoustic waves, avoid the solar center. So it would be good for exploring more precisely the solar center to have a different type of waves, which are called gravity waves, like the waves on the sea, which have this kind of trajectories. So, of course, we have been looking for these waves from the very beginning, but if these waves would give us much more important, detailed information on the solar core, they are confined inside. Sorry. These are visible at the surface. These are not visible at the surface because they are inside. So we astronomers, we helioseismologists, have been trying to hope that I'm very bad with this, sorry. Peut-être. Non mais j'ai besoin de ça. I will get used before the end, maybe. So we have been hoping that some of these waves will still move the upper part a little bit, and that the instrument that we have put in space will be able to see some millimeter motion on the solar surface, which could be attributed to these gravity waves. It's been sometimes partly successful, sometimes doubt, sometimes certainty, sometimes doubt again. And what I propose you today is a real certainty. I will see if I can convince you. So our story started, my story personally started, look, in 71. 71 was my first publication with François Rodier of the concept of the instrument with sodium cell. This sodium cell is like the potassium cell of Mark I. You know this, I don't have to spend too much time on this. A few years later, this sodium cell became the core of the Golf instrument, which is still flying on SOHO, somewhere, at 1.5 million kilometers from here. And this has started working in 96, spring of 96, while in spring of 2017, so it's been working for 21 years now. From this, many people have tried to extract some G modes. Gravity waves are called G modes. And speaking of G modes, I'll show you P modes, and I will tell you why. G modes are, this is a spectrum of P modes obtained with our network IRIS, Pierre was telling you about. And this is the same spectrum obtained from Golf. It's the same, just a little bit more accurate with this one. And the little bit makes a big difference, of course. And I go a little bit further, I will come back. This is the same Golf P mode, in which I want to show you the frequency range of the G modes. The P modes are mostly around 3 millihertz, which means 5-minute period, 300 seconds. The G modes are supposed to lie here, below 0.3 millihertz, which means periods typically longer than 1 hour. And you can see that the observation in this range gives an increasing noise, which is increasing then very far. And we know, we are pretty sure that the amplitude, visible amplitude at the surface of the G modes are much smaller than the amplitude of the P modes. The P modes are progressively lost in noise somewhere here, and we are looking for smaller amplitude there. You see the difficulty. So What I had in mind for many years already, and I was not alone, of course, is to use the P modes as a tool for detecting G modes. The P modes, some of them are crossing the core, some are crossing the core directly, which are the radial modes, some are crossing part of the core in turning around, and if the core at the center is doing something like that, it should produce some modulation on the P mode frequencies. So this has been in mind of several people from 20 years at least. It has never really been successful for one obvious reason. The P modes are mostly sensitive to the upper part of the sun. The upper part are shaken by the convection. So the P modes have not a frequency which is absolutely infinitely defined. It has a frequency which has a given range, like 1 microhertz for 3 millihertz period frequency. There is a 1 microhertz line width, and this 1 microhertz line width basically forbids to detect any modulation provided by G modes, because it just, I would say, the modulation due to the surface noise is much too big compared to the tiny modulation produced by G modes. So we have tried again, never success. So what I had in mind and what I finally succeed to do is to use a differential parameter of P modes. We know that P modes, some of them have almost an identical structure. They're identical in the upper part and they would differ inside. For example, do you all know this Echelle diagram? Maybe not. Maybe not. Echelle diagram is something I invented. I'm proud of this. During a coffee break in October 1980. During coffee break, I was thinking of how I could represent a figure in which we see that these P modes are almost equidistant, and how I could represent a figure which shows the almost. So I took a piece of paper. In this time, we did not have computer. I had a list of numbers, which was the number of the frequencies of the P modes on a sheet of paper, numbers. I have a piece of paper, I have a pencil, so I draw lines and I put the frequency by hand on line by line, and I saw something like that. So, wow, it's not exactly equidistant, because this is then one range of frequency in microhertz, and range after range you are looking at all the P mode spectrum. If they were exactly equidistant, you would have vertical lines. They are not exactly equidistant, so you have almost vertical lines, but not quite. And these are showing the modes of degree 1, degree 2, no, degree 0, degree 2, degree 1, degree 3. The P modes have a degree, which is the geometry of the mode. And the equidistance is measuring more or less the diameter of the sun. But the small difference of frequency, like this one, is provided by the small difference of structure of the mode of degree 0 and the mode of degree 2. One is crossing the solar core, the other one is just avoiding the solar core. And all the upper part of the mode are identical, which means that this small difference here is mostly a measurement of what's inside the core. So my idea was, this is a parameter that we have to use to measure its modulation, since this parameter is measuring the solar core. If it is modulated, it will be modulated by the solar core and not by the solar surface. The problem is obvious. This is very small. It is 10 microhertz. The inverse of 10 microhertz is 1 day. So for measuring this, you need a time of integration of at minimum 2 days. And in 2 days, you cannot access to the G-mode of 1 hour period. Not even to G-mode of 1 day period. You can only access to G-mode of period longer than 2 days. And for many reasons, the reason is that at such long period, if G-mode exists, they will be piled on each other. You cannot detect them. So we have to find another parameter. The other parameter could be this distance here. This distance here is the distance between frequency of G-mode of P-modes of degree 1 and 0. So these are not completely identical in the upper part, but they are still very close, and they are quite different inside. This is called, in Astroseismology now, the large separation. And the large separation is still a parameter which is very sensitive to the core of the star. And it is also a little bit sensitive to the upper part, but less. So I decided, okay, I cannot use a small separation because it does not give me access to short periods. I will use this large separation, and the large separation is supposed practically to measure the time. It is a inverse, it is a frequency inverse of a time, and this time is a travel time of a wave which is from solar surface through the core and back. 2 times the diameter, and this is measured by this difference here. So measuring the travel time as a function of time through the solar core during 15 years, 16 years, I have used 16.5 years of Gulf data for that. Measuring this time, if the solar core is shaken, this time has to be shaken a little bit, and if the solar core is shaken by G-modes, this time will be shaken by G-mode frequencies. To measure this, still you need at least 8 hours of integration. 8 hours means that it will not give you access to periods shorter than 8 hours. Periods longer than 8 hours for the G-modes are already very long period, because the first are around 1 hour. So it is a frequency range that we call asymptotic, because the G-modes of so long periods have asymptotic properties, and these asymptotic properties, I would say, present one major advantage. The major advantage is asymptotic approximation, which means that we have some regularities that we can exploit to pile the modes on each other and see if they would get out of noise. And the drawback of this is that nobody knows how this mode can be excited. These long periods, what can excite them, we don't know. So my thinking was, okay, we don't know, but maybe. So maybe I try. I try and we will see. So, okay, one of the main motivations is indeed the solar rotation. We know a lot now about solar rotation thanks to helioseismology of P modes. You know that, again, in the upper layers, the rotation is very much differential. This is rotation speed, and this is radius, surface, depth of convective zone, radiative zone, and below. So we know the rotation very precisely in the upper layer. It is differential down to the base of the convective zone. There suddenly, in this layer, which is called the tachocline, it becomes rigid down to the limit of the solar core, and below nobody knows, because the P mode do not permit to measure the rotation inside the core. That's main limitation. The best possible inversion of the P mode splitting, which means decomposition of one frequency by the rotation, could think that possibly there is a beginning of increase, and possibly the core would rotate faster, maybe. But with the P mode, we don't know. So, as I wrote, we definitely need G modes if we want the solar core rotation. And the G modes that I will show you are located somewhere here. Only in this range of frequency where the G mode cannot be accessed in the direct Gulf signal, because it is a part where the noise is increasing a lot. So no way you will not detect G mode directly on the Gulf signal. And then the idea is to detect in the sequence of P mode to see if they are doing this. This is the idea. So the asymptotic properties, because this range is asymptotic, I will use completely the asymptotic properties to detect the G modes. The asymptotic properties are that probably for one given G mode degree, the rotational splitting should be independent of radial order. So the splitting of all modes should be the same. Each G mode frequency should be split by rotation in a triplet for L equal 1, in a quintuplet for L equal 2, and this splitting should be the same for all modes. So my first idea, okay, I don't know where are the frequencies, but if there are, they're all the same splitting, so there should be a lot of triplets and a lot of quintuplets. So the best idea is then to make an autocorrelation of a spectrum. If you have many triplets, you will see a peak of correlation somewhere. And the second asymptotic property which is of interest is that these G modes are equidistant in period. Of course, we are computing power spectrum in frequency. But if we know frequency, we know period, so we could take advantage of this assumed equidistance in period to try again to pile all modes on each other and to see if we can see something. So I will show you how it has been successful to first detect the splitting of rotation and then to detect the asymptotic equidistance in period. Of course, we are not the first to look for G mode. I told you this story started 41 years ago, in 76, when Severny, Côte and Sap in Crimea published a paper saying we have seen the sun oscillating at 160 minutes, 2 hours and 40 minutes, and roughly we don't understand what this is. The interpretation of this phenomenon seems to cause much theoretical difficulty, indeed. So this was a long story. I will not tell you about this long story, but it was a long story until it was more or less never 100% proved, but at least everybody convinced that this was an artifact. 160 minutes is one harmonic of 24 hours, and there was something like that. Since then, many other publications have been tried on the G mode, and the most recent one, which will be accepted probably this afternoon, it has been accepted last week with minor revisions. So minor means that we can do it. This is it, and now you have already, with this title, one of the most important results is that the solar core is rotating faster than the rest. So what I've used is indeed 16.5 years of Gulf data. This is a 16.5 years of Gulf data, including the gap in 98 when SOHO was lost, and including the change of sensitivity of the measurement when it was necessary to change from one side of the measuring line to the other side. But in my measurement of oscillation of the large separation, all this disappears. You will see. I have some reference of people who are, some of them are here, who have already tried to measure the splitting. And this is a paper of Rafa. A stable splitting around 850 or 900 nanohertz has been found. And unfortunately, the splitting I will show you is not consistent with this one. We will see. In the same paper, or another paper, Rafa published also this estimation of the asymptotic equidistance around 24-25 minutes for the modes of degree 1. And this I will confirm. We find 24 minutes and something. So my method, I detail, is first to identify the differential parameter I told you, the large separation. Then select an optimal frequency range for measuring this. And it cannot be measured on all the P-mode frequency range, because all the P-mode frequency range contains the high frequency, and in the high frequency the P-mode are shaken too much by the surface. So we have to avoid the higher frequency. We also have to avoid the lower frequency, because I will measure this large separation on 8-hour database. In 8 hours we have not the sensitivity of 16 years, and if we want to see the lower frequency modes, in 8 hours we cannot go too low in frequency, or we are lost in noise. Then, as I say, it takes 8 hours, and I made a sampling every 4 hours to have 1 8 hours, the next 8 hours like this, the next like this, the next like this. So there is some oversampling, some over, yes, to make sure that in the power spectrum I will have access to frequencies up to 8 hours, 1 over, which are damped by the filtering, but we're still there. So my frequency range has then been selected first to avoid the high frequency up there, because these are too much sensitive to the shaking of the surface. To avoid the lowest frequency here, because they are small amplitude and in 8 hours they are not visible. And there is a third reason. Third reason is that in between you have this, which is almost a straight line, which means that the large separation is precisely defined much better in this range from 25 to 15 here than it would be by taking account of this where it is different. So I made all this limitation to make sure that I will limit the noise on my measurement of the large separation. So I spent 1 year on this to adjust until I'm sure to have selected the parameter which is producing the minimum level of noise on its measurement. So the idea is the following. Working between 2.3 and 3.7 millihertz, this is a mean spectrum of 34,2061 samples of 8-hour periods. Each one of these 8-hour periods gives a spectrum. This is the average of these 34,000 spectra. To make sure that I will use all the range to measure this distance here, I divide this by its mean envelope. Approximately, that's enough to make it looking like a sine wave. And then I will measure the frequency of the sine wave. This is frequency, so the frequency of the sine wave, the frequency will be a time. And this time is indeed the 4-hour travel time of a wave from the face to the other side and come back. So this is just one example of a 8-hour power spectrum. Each spectrum of this gives you one main peak. This main peak in time is at about 1.5 10 to the 4th, okay, 15,000 seconds, which is 4 hours and a few minutes. And so this time here, so the abscissa of this is now my data. Every 4 hours I have one number, which is this, 14,800 seconds and something. This is another number 4 hours later, and so on. So I have 8 hours of this number every 4 hours, and this is my data that in which I will look for G-modes. So this is the data, 16 years of this measurement, at least of fluctuation of this measurement. The standard deviation is 52 seconds. The mean is not written here, I forgot. It's okay, 4 hours, 6 minutes and a few seconds. And this is these fluctuations that I will study now by Fourier analysis and look for G-modes. I show you immediately the power spectrum of this. So remember, this is the first 0.5% of the Gulf spectrum in frequency, the extreme lower part. All this is the 0.5% of the frequency range of Gulf spectrum. And you can see that in the Gulf spectrum, it was moving up very quickly to high levels. In this case, it's flat. Everything which is noise in Gulf is cancelled here. It is flat, except for the very lowest frequency, which are not of interest because these are several days of period, several weeks, several months, several years. We are not interested in this. What I will study is this frequency range. This frequency range because, first, it is a flat spectrum, so I don't have to deal with 1/f noise. And second, this is the limit under which there is absolutely no hope of seeing G-mode because they are all piled on each other. So my first attempt then is to take this range and to compute the autocorrelation of this spectrum. If this spectrum contains many triplets for L equal 1 and many quintuplets for L equal 2, I don't expect more, I will see, I should see in autocorrelation some peaks seeing this equidistance, this equal spacing of splitting. One evidence that this measurement is very little sensitive to what happened at the surface is this. This is the lowest part frequency. It is here, in the first millimeter here. You have here the frequency of a solar cycle. You don't see a signal at the solar cycle frequency. You have here the frequency of the 1 year rotation of the Earth, which is 31.7. You have no signal here, and we know that the satellite is orbiting in 1 year with elliptical orbit. We have no signature of the orbit. We have no signature of the solar cycle. So we can say, okay, we are not polluted by any velocity information. We are only measuring the time of travel of sound waves. No pollution. So this is what I told you, the autocorrelation of the spectrum in the frequency range from 5.5 to 34 microhertz. And when I saw that, there is a beautiful peak here, which is at 210 nanohertz. 210 nanohertz is close to half the splitting rotation of P-modes. So when I saw that, I said, wow, okay, I have the proof the solar core is rotating as same speed as the surface. But then we had to think. We had to think because we have to remember to measure things in sidereal unit. And with this measurement, which is using the P-modes as a tool, and not the instrument which is on Earth, and not the instrument which is on Gulf, it is using the P-mode. This P-mode is the instrument for measuring. So we had to think during, I would say, a few weeks or even a few months to understand what we were doing. Because this is the same thing with artificial data. Fix Schmieder has produced a fantastic series of artificial data set reproducing all the detailed properties of golf, including the change of sensitivity and the noise, the gaps, everything. And the artificial data do not show the three main peaks that you have seen in here. I will exploit now this peak, this one, and this one. So this is convincing at first sight. These are not, but you will see that they are still, and none of these three peaks are visible in artificial data, which means that they are not produced by some bug in the analysis itself. Now, I come back to the equations of the splitting. The splitting generally is proportional to the tesseral order, is proportional to the rotation, but for the G modes there is a Coriolis coefficient, which means that for the splitting of the degree 1 you have to divide by 2, and for the degree 2 you have to multiply by 5 divided by 6. And to get it in sidereal unit, you need to subtract the rotation frequency of your instrument around the Sun. And generally this is taken as 31 nanohertz, which is 1 year period of your instrument on Earth or of golf in space. It's still 1 year. But we are using an instrument which is inside the Sun. It is a P mode. And the P mode are not rotating around the Sun in 1 year. They are rotating inside the Sun in 4 weeks. So this 31 nanohertz usually used here has to be replaced by 432, 433, 434 nanohertz, which is the rotation speed of the P modes. And that is, of course, changing everything. My first idea that the 210 nanohertz peak would be measuring the constant rotation is totally wrong. It is measuring something else. But if we still interpret it as an evidence for the rotation of the L equal 1 G modes, because they have the best chance to be the most sensitive to what we are measuring, then we have to think of this. If we see this equation, the splitting of the mode of degree 1 is to be seen as the frequency of the G mode divided by 2 minus this number would be negative if the G mode were rotating at the same speed as P modes. And what means the negative splitting? It just means that, and the autocorrelation does not see the difference. Positive splitting or negative splitting for the autocorrelation is just a pair of peaks. Which means that when we measure one splitting of G mode, we don't measure directly the rotation of G mode because we have an ambiguity between negative or positive splitting. For example, for our 200, it is 209 nanohertz, the choice of these two values here, which can give plus 209 or minus 209, is either an almost rigid rotation, just slightly faster than the P modes, or a very quick rotation, which is 3 times faster than P modes. And to choose, we need the degree 2, because the degree 2 has a different Coriolis coefficient, so it will help to eliminate one of the two solutions. So I will show you. If we have the slow solution, the degree 2 should have a splitting of minus 60. Minus 60 means 60, it is somewhere here. We don't see anything significant here. If the solution is a fast rotation, the splitting of the degree 2 should be 630 about. 630 is this peak. And 1260 is this peak. So at this level, we are very much tempted to think that, okay, we have a signature of splitting of degree 1 and of degree 2. The other in autocorrelation are lost in noise. But these two are very tempting. So what we can do is, okay, let's assume that we have indeed some signature of G modes in this, and let's play to the a plot of G mode frequency, and as a function of G mode frequency, we will plot the sum of splitting of the degree 1 and splitting of degree 2 to see if we see some peak, beautiful peak or not. And the reply is indeed yes. Sorry. Indeed, plotting the value of the autocorrelation for 1, 2 first and 2 second splitting, we can find indeed a fantastic peak at 1280 microhertz, which means about something like 3-day period. No, not 3 days. This is 3 times faster. Okay, about 10 days, 8 or 9 days period. And what's now? I have much more to convince you, of course. If we take only half of the 16 years data set, I should arrange this. I'm just sitting on the cable, that's why. Where is my... Here. Taking half of the data set, you can see that we can... These, the autocorrelation peak are getting less visible, but the 3 of them together still give a beautiful high fast rotation peak. And if we compute this separately, the rotation of G modes by the equations, separately for the L equal 1 and for the L equal 2, you can see that, for example, the blue is L equal 1. You can see that you have no information if the rotation would be 800 something, in which case the splitting would be 0. Because 800 divided by 2 is 400, 400 minus 400 gives 0. So you don't have information for rotation around 800, but on one side or the other side, you have symmetrical situation, a peak of slow rotation, a peak of fast rotation. This is the ambiguity I was mentioning. And for the L equal 2, in which the lack of information is not at 800 but is at 500 something, then you have no ambiguity, and one of these peaks is sending here exactly at the same place. So this is very convincing. You have a fast rotation of 1280 nanohertz. But I still have a lot more to tell you. The lot more is now the search for the asymptotic equidistance in period. So asymptotic equidistance means that you have, I take that it's certain I have the signature of many modes. Many because they give me this signal in the autocorrelation, so there are many for this. They are not visible one by one. I have tried for days and days and days. No one is visible one by one, but taken collectively, a large number of them, they give the information. So if there are many, I could possibly detect the equidistance in period. So I have to make a model. I select one hypothetical period, equidistance, and I have two unknowns in this problem, the equidistance and the position of one of them. If I know one of them, by equidistance I know all of them. So I need to know one of them and the equidistance. So we have a problem with two unknowns. So So I can make a model and scan two possibilities of the two unknown and look if somewhere I will find a peak of correlation between my model and the spectrum. This is easy to do. It's a two-dimensional model, so it's a two-dimensional figure, and it takes at least 20 seconds to load because it's a big figure. So just wait for 20 seconds, no, 10 seconds, okay. So this is a model of 76 potential G-modes, equidistant in period. I have tested a large range of possible values for the equidistance from 1,400 seconds, which is 23 minutes something, to 1,520 seconds, which is 25 minutes something. So a range of 2 minutes from 23 and something to 25 and something. And I have tested initial possible frequency period from 30,000 seconds to 32,000 seconds. If one of these combination give me the position of my triplets on the real position of G0 triplets, I should see a peak. And you have a beautiful peak here for equidistance of 1,443 seconds, and 1,443 seconds later you see a second peak because you have the same equidistance moved by one step. And we could prolong this figure many steps, and you will still see peaks equidistant by 1,443 seconds. So at this level we are almost convinced that we have the splitting and the equidistance, and we can still do more. From this previous figure, this is just the list of maximum value line by line, which means that here the abscissa is what was the ordinates of the previous figure in color. I test from 30,000 seconds to 32,000 seconds. What is the maximum of my line, to see how this red spot on the color figure is quantitatively. And this is it. It is really a very sharply defined peak. This is not even above the mean level of noise, which is here, because this is showing each maximum of each line. So it is above the mean level of maxima of line by line in my general noise. So it is extremely convincing. Now I can do even better. I assume that indeed I have equidistant G mode in periods, and I assume that I don't know the splitting. I can do that just for playing a game. I know the splitting, but I assume I don't know. So I will look to play this game with only the central frequencies of the G modes, since in this method the central frequency is visible. So I assume only now 76 periods in which I don't take into account the split components. And this is the same game, playing same as this figure, just replacing the model by 76 central frequency instead of 76 triplets. And with 76 central frequency, you have not so good signal-to-noise ratio, but you still see the equidistance exactly at the same value, which means that the method sees the central frequencies of the G modes. We can measure the central frequencies without the knowledge of the splitting. Then I have 76 central frequencies. I can take 76 layers of my spectrum, pile on each other, and see if it will show me the splitting. This is it. Of course, it's not showing with a large signal to noise, but in this I did not take into account the knowledge of the splitting. I just piled 76 layers of spectrum, and this is plus or minus 209 nanohertz. So the splitting is directly visible on the signal, not going through the autocorrelation. So just a few numbers. The equidistance is then 1,443 seconds within 1 second, even within less, you will see. The first period is known within a few seconds. Then the frequencies are known. And you have to know that the G-mode separation in the lowest part of the frequency range is 5 times smaller than the width of the splitting. So they are piled on each other, the G-mode. This is not a problem in the autocorrelation. It will still see the separation. But it makes more difficult the measurement of the modes themselves through the equidistance spacing, because then you are piling out many things which are different. This is why, for this, I did not start from 5 microhertz, but from 7. If I extend my analysis down to 5 microhertz, the signal is getting less visible. But I have still 76 G-modes contributing to this analysis. Then, the same for L equal 2. It is possible, I will tell you just faster. L equal 2 has less signal. You have seen that the peak in autocorrelation are smaller, despite the fact that they are quintuplets. So autocorrelation to a quintuplet has much more pairs which are contributing. Because if you take 5 peaks, you move by 1 unit, you still have 4 of them which are coincident. So if they would have the same amplitude, the peak of L equal 2 will be much higher in the autocorrelation. It is smaller. So the amplitude is much smaller, so the detection of the periods themselves is more difficult. But we know precisely where it should be, because the asymptotic equation does not leave much freedom. If we have this 1,443 seconds equidistance for L equal 1, we should have 833 seconds for L equal 2, plus or minus a few seconds. So I have looked around 833 in a more limited range. And you have these peaks of correlation at 833.8, which is close enough to 832.8. This is peak. And same here, so on. So this is potentially convincing. The same analysis by scanning horizontal lines show it with still a reasonably good signal to noise. And now, where I will become even more convincing is to take the 16 years of data and to cut it in two. The first 8 years and the second 8 years. These two 8 years data are 100% independent data sets. The same analysis made on the 8 years on one side as the next 8 years. This is for L equal 1, and this is the equivalent of this figure. Yes, we have to pass the slow. Okay, the equivalent of this figure exactly on separating 8 years and 8 years. Just a few seconds. Here. Of course, okay, 5 minutes. The signal to noise is much less in the 8 years, but the peak of correlation in red is the first 8 years, in blue the next 8 years, or the opposite, I don't remember. And the peak of correlation is exactly at the same place. And this is for two data sets which are 100% independent. So this is 100% convincing now. The same has been done for L equal 2. And this is another game. Just, I would say just for fun. I assume that, okay, I have the signature of G modes in my spectrum. I will assume then that I have the splitting of G modes. I don't know the splitting, and I will use the equation assuming that I don't know either the splitting of P modes, 433. And I've played the game, can I retrieve the splitting of P modes only assuming that there exist G modes? And I don't know the frequencies of G modes, I don't know the period of G modes, I just assume there is G modes. And the reply, I don't enter into detail. This, I played a lot with this. And the reply is yes. With only the assumption of G mode exists without knowing where they are, I find a peak at 433, which corresponds at this parameter in my equations for the P modes. So this is another convincing step for me. And the last step I did is to look for the slight departure from asymptotic total equidistance. Because Janine Provost and Thierry Corbach told me that in this frequency range at 8 hours, you are not yet completely asymptotic at the level of accuracy that you pretend. So say, okay, I test. I introduce an asymptotic departure from asymptote, hyperbolic term. I adjust this hyperbolic term to improve my signal to noise ratio in all my figures. And then I play the game of showing the triplet, and this is triplet with a better account for its slight departure of equidistance. And so you see plus or minus 209 nanohertz triplet of L equal 1. So I will stop here. My conclusion is that the mean rotation rate is for the G modes 277 plus or minus 10. And the plus or minus 10 is fantastically accurate. This leads to a mean rotation inside the core itself, because the G mode kernels go still a little bit inside the radiative zone. It would mean a mean rotation rate of the core itself of 1644 plus or minus 23. This plus or minus 23 includes some more uncertainty on the kernels themselves. The equidistance is this number taking into account the slight departure. The real equidistance is slightly different. It is 24 minutes, 3 seconds, 0.6 within less than 1 second, 332.8 within less than 1 second. And this provides a parameter of theorist, which is a P0, which is supposed to be around 34 minutes. It is 34 minutes, 1 second within 1 second. So I can tell you these numbers are so accurate that Jamil told me, we cannot use this number, this is too accurate. We can never find a way to test our model at this level of precision. I said, okay, that's your problem. My problem was to give you numbers. I give you numbers, now it's your problem to find a good model. And I suppose it's enough because it's time to stop.
Thank you, Eric, for this interesting talk. We have time for one question.
One question?
Yeah, because we are very late, actually. The gainer.
Great talk. Sorry that I only taught the last 10 minutes. But how does it compare to red giant core rotation? What is the conclusion you draw in the comparison with rotation from red giants?
Sorry. Can somebody repeat?
Okay, I do it. What do you? How does it compare to a rotation from red giants? What do you take from it?
Rotation of what?
Red giants. Gigantes Rouge.
Red giant.
Oh, giant red. I don't know.
Talk about it overnight.
Okay, yes. No.
Yes, sorry, it's half a joke, half not a joke. We all assume that the rotation, the sign of the rotation is the same in the core than in the upper zones. I mean, it's 4 times faster in the same direction, not the opposite.
Yes.
But I mean, you see that in your analysis or not? You see the sign of rotation, but that's a fundamental.
That's an interesting question. It's not an hypothesis that what we have considered, but if the core is rotating like this, that will make some turbulence between the two, I suppose. No, if the rotation was in opposite direction in the core, of course the equation would provide different result. Yes. But this is so much unlikely. Already, now we have a problem, which is what is giving power to the G modes, because they are small power, but there are many. So there is some power in this G mode business. What is giving energy to these G modes? My idea of observer, not theorist, is that if the core is rotating fast and just above this rotating slow, there is again a kind of tachocline, and that must be turbulent, and that maybe that when I am on the beach, I see the sea, and there is wind, so the sea is not moving, the wind is moving, it is creating waves. So I think, okay, the core is moving, above is not moving, or less, so in between it must be creating waves. So maybe this is a solution, I don't know. But this is the only problem for tourists. I give numbers.
Okay, I think that we can stop here. Thanks again, Enrique.
Thanks to you.